ways in which it can be interfered with are very complex, but how do they actually learn? How does a neural network learn to organise itself so that it's thinking in the right way, if you like? And this was a problem that was first solved mathematically. So before they decided what types of process they were looking for, the scientists had to ask themselves, well, what type of process would actually allow a neural network to self-organise? And some of the experiments involved simulations of neural networks. And, of course, but to begin with, some of them are actually mechanical. So there's a wonderful story of how people put together in America a neural network using bits out of B-52 bombers and things, and gyros and all the rest of it. But what they found was that a simple neural network like this one, where you've got 3 inputs, 2 outputs, each of these circles represents a neuron, actually can self-organise itself in an intelligent way, inverted commas, if it has the right mathematical rule in terms of how each neuron is behaving. What is that mathematical rule? And we'll do that in the next slide, but in this particular simulation, applying this mathematical rule, you can see we start getting almost a human-like learning curve. And that's achieved by putting possible inputs onto here and clamping outputs onto the output, and then asking the neural network to reorganize its weights, the efficiencies of its connections. And if you do that enough times, after a while you can take the outputs off, and whatever you put on the input, the network will be trained enough to produce the appropriate output that you want. So here you could have the amount of red, white and blue in a flag, and over here you could have the nationalities perhaps that flag represents. And if you put on enough examples of the amount of red, white and blue, eventually it will be able to identify some of these flags. Well, better to say red, blue and green, wouldn't it, I suppose? Primary colours or whatever, yeah? So it can train itself up if each neuron has the right mathematical rule. And the person that really is best known for having thought about that problem and thought about what that mathematical rule is Donald Hebb, and that goes back to 1949. And his rule was basically that if the postsynaptic neuron is already firing when the presynaptic neuron is releasing transmitter, then the synaptic efficiency has to be increased. Okay? So what we really look for here is a coincidence detector. So that if if this one is already firing a little bit when another one is already firing onto it, then the efficiency will be increased. That's called a Hebbian synapse, that simple mathematical rule. And if you apply that mathematical rule to that simple neural network, where they had about 6 neurons in it, then it appears to be able to learn. It can self-organise itself. Well, that's all very well. So in 1949, we already knew that if neural rule, this type of coincidence detection, then they could organise themselves in an intelligent way. And this type of coincidence detection is quite often it's quite often talked about as neurons that fire together, wire together. It's a very simplistic way of putting it. Nobody knows who ever said that. It's often attributed to Donald Hebb, but he never did actually say that. But it's an easy way of thinking about it. Neurons that wire together, fire together, or fire together, wire together. Okay, so what's the biological process by which that could happen? Well, the best candidate that we have, the one that we think is most responsible for this, is long-term potentiation. There are other types. Long-term potentiation is an enduring increase in the size of the postsynaptic potential. And to try to, the first detection of this was actually in the hippocampus, a part of the region of the brain consolidating memory, the hippocampus of rabbits, but we now know it's common throughout the brain. And what I love about the way in which it was discovered is the almost haphazard sort of sense of it. Lomo later said, "As for me, it was certainly not prior interest in possible memory mechanisms that led me to a discovery that was in some ways accidental, in other ways the result of an intuition that as often I felt brought me to look for or see phenomena that turned out to be new and interesting." So they were really just messing around. They had an intuition that maybe this could be the case, so let's see what happens if. And they found that, yeah, actually, you can make a neuron in the hippocampus of a rabbit increase its postsynaptic potential. And this is the sort of experiment that they did. So when we're talking about postsynaptic potential, we often abbreviate it to EPSP. We're talking about an excitatory postsynaptic potential. We're not going to talk about inhibitory connections, but it's basically the same process, but in an opposite way. And what they did was they were providing, they were measuring the EPSP, that's the output of a particular neuron here. So let's say we've got a particular neuron here and they're recording it, they're recording the output of this neuron. And they put in a stimulus, and as soon as they put in the stimulus, of course you get an increase in the output of that neuron. But maybe that's surprising because it's just transmitting the stimulus, so maybe that's not that interesting. But what was interesting is that afterwards there was an enhanced, a sustained enhanced activation of that neuron. So this was the first evidence that we had that neurons, an individual neuron, can learn, if you like. And I'm using the word learn in a very primitive sense, the idea that some environmental change can influence its behaviour in the longer term. The environmental change being an electrical stimulus, and the efficiency, the change in the neuron is now that it's actually outputting more electrical charge, more action potentials, essentially. Yeah, we have to be careful about this as well, that when we talk about the increase of a neuron, the output of a neuron increasing, we're talking about an increase in the frequency of the action potentials. We're not talking about an increase in the magnitude of the action potential. We're talking about, because it's always the same, it's a blip, it's just a click, it's an impulse. When the output of a neuron increases, it's an increase in the frequency of those action potentials. So this was very exciting. And of course here you're talking about just one input into this neuron from this stimulus, but actually, as well as single pathway stimulation, you could have weaker multiple inputs adding together and producing the same effect. So you could have like three electrodes going in and stimulating the neuron with much less voltage in each of them, if you like, much less electric charge in each of them, but you still get the same effect. So that's, there's a sense in which it can be additive. But the really important thing, and they've found lots of different long-term potentiation types, and one of the ones they've found is the Hebbian long-term potential, where when you've actually already got the synapse firing and you're inputting electrical charge onto the neuron, you get in. But if you ask 100 neuroscientists on the street, what is the basis of human learning, they will say long-term potentiation, and particularly Hebbian synapses. So how might a Hebbian synapse work? Well, there are different mechanisms. I'm just going to talk about one of them, the most famous one. And in a minute you're going to be explaining this to your neighbour as well, so I will try to do it properly. Normally, this EPSP, this excitatory postsynaptic potential, in other words, what comes out of this postsynaptic neuron when you put on an electric potential through the presynaptic terminal, it is dependent on these AMPA receptors. Okay, so that's normally the way in which it works. There is another type of receptor. These are glutamate receptors. There's another type of receptor here, which is called an NMDA receptor, functioning normally. But when sufficient incoming glutamate binds to the AMPA receptors, so you've got glutamate binding onto here and allowing these ions to pass, when there's sufficient happening here to be causing this thing to be firing and to be lowering to be changing the postsynaptic membrane, depolarizing it, actually making it more positive, I apologize, making it more positive, depolarizing it. So when this is happening strongly enough for there to be a depolarization in this postsynaptic terminal, then that can actually dislodge these magnesium ions. And when those magnesium ions are dislodged, then we've now got another set of a different type of receptors that are open for business, that are open to be stimulated by the presynaptic terminal, by glutamate arriving at these receptors and causing changes in the postsynaptic terminal and contributing to this action potential. But that only happens if you've got synapses coming in, electrical charge coming in to the AMPA receptor when this is already depolarized. So that means for this to be already depolarized, well, it could have happened here, but it could have happened on another synapse or somewhere. The important thing is that this neuron is already in a state that is of stimulation. So when you start stimulating a neuron that's already in a state of stimulation, you've got the basis for your Hebbian synapse. You've got the basis for coincidence detection. And it responds by increasing its efficiency by opening up these NMDA receptors as well. Because this depolarization brings the magnesium ion out and opens up more receptors for business.
So more glutamate is going to came in the postsynaptic?
So the glutamate is the neurotransmitter that's come in, and normally it's operating on these, but because this is becoming depolarized, the magnesium ion gets shoved out and the glutamate can now operate on these as well.
So it will be more glutamate?
Yes. But most importantly, an increase in the depolarization of this postsynaptic terminal. More receptors operating, essentially. Yeah?
Sorry if this is not really a question. What makes some of them both be activated at the same time and some only one of the presynaptic? If you understand what I'm asking. Why
Well,
some are Hebbian and some are not Hebbian?
One of the reasons why this neuron might always... Well, because you need both types. Because there are particular purposes that make a synapses are not just about learning in the way that we're interested in. The brain has to do a lot more than that. So non-Hebbian synapses have their own role as well. That's why we're just focusing on the Hebbian one. But the reason why this might have become depolarized is not just necessarily because of what's been happening here, but that other synapses from other neurons have caused it to become depolarized. Yeah?
Presumably there's got to be an origin.
Well, like an initial neuron that starts the whole chain off. So those are peripheral neurons. So, for example, that's the main input to the central nervous system. So your eyes have neurons at the back that are sensitive to light. And it's the light, in that case, that starts the action potential off.
But apart from that, it'll be connected. Action potential is always caused by something else.
By another neuron, yeah.
And another question, can it happen in reverse? Because rather than the increase of potentiation, a decrease?
Well, whether it can happen in reverse is a good question, because most of the artificial neural networks actually work on a process of back propagation where information is communicated back through the network. But as far as we know, neurons don't work like that. So we're still, so that's why That's why a lot of the maths in the artificial neural networks don't line up with what we know in the brain. When the brain wants to do something different to excitation, it uses inhibitory synapses.
By reverse, I don't mean going from there to there. I mean reducing the action potential frequency.
Yes, so that would be an inhibitory synapse. So it could be, serotonin, for example, serotonin receptor, that would probably inhibit so it makes it less likely that the next neuron is going to be firing and actually reduce the firing rate.
Are any obsolete then?
I have one question up, and then there's two, and now there's it's sort of like they're escalating. I hope it's not because my explanations are poor. Let's go on.
So you talked about the efficiency of
Yes.
Would some potentially be missed out or left alone and not used again?
Would some what be left out?
The whole process of the actual neuron itself, because you said there's lots of them, aren't there?
Yes, there are different. The connection between both neurons is strengthened. Yeah.
Once it's gone out of the pre-synaptic neuron.
Well, of course, there's nothing stopping this neuron from being connected back into that neuron via a longer circuit. Yeah. Yes.
So when you say Hebbian synapse, is it a physical state of having that extra receptor, or is it? Do they all have this receptor, and then some of them are able to activate it? What is
The Hebbian synapse is.
Is a Hebbian synapse? Sorry, is it a process or a physical thing?
It's a physical instantiation, that allows a process to occur, but it's only one example of a type of synapse. It's one class of synapse.
So from the inception of that particular synapse, that extra receptor was there already?
Yes.
Because when you talk
Yeah, but hang on, I haven't finished yet. Because I think what you're saying is, how does that change anything in the absolute long term? Because you can see how this changes things temporarily, but it's not going to change things in the longer term. And I think this is a good point. So let me go on to... Oh no, I was going to ask you to explain to each other first. Okay, but so this is just one of the stages to form a synapse. And in fact, there are longer term changes that ultimately can bring about the production of a new synapse entirely. And that's when learning is probably going to become more consolidated. But for the moment, I'd just like you to explain what I've just discussed to each other. On the other side of the paper.
discussing this, it's polarization. Them sticking to the receptors there, maybe. They were thinking of a party here.
Right. Okay. Yeah.
Open it doors. It's like a bit of a rave going on because of depolarization.
If it helps, it's good.
We were wondering about the coincidence detector and the coincidence itself.
Yeah.
Do we actually understand that correctly? That the coincidence is this synapse or pre-synapse is firing,
Sorry.
while this is the polarized.
It's already, yeah, that's right.
that's the coincidence.
Because another neuron has probably already started to depolarize it. So there's a coincidence that this one is also trying to depolarize it.
Right. Okay. So that's the coincidence.
That's
and then,
coincidence.
Can I call this coincidence detector this receptor here? Because it depolarizes only if magnesium is released. It's not blocking this receptor, right? So can I say that the detector is
So this could be already depolarized because another neuron is trying to fire it.
with a detector?
Well, I suppose you could say yes. No, you could say that's the coincidence detector. Yes, because that's the thing that happens. Yeah, that's the thing that signals, if you like. That's the first thing you see.
Yeah.
So that's the first change that happens. Yeah.
When you
Yeah.
depolarize it.
Yeah.
Oh, okay.
Fair enough.
Yeah.
We okay? You're looking concerned. You alright?
Oh no, we were just thinking about experiments.
Oh well, that's alright then. We're alright? We're okay? Good, good. Yes.
And the question was, is it replaced shortly after it has been gone, or does it stay away and the receptor is open?
Yeah, so it will come back. So once things settle down, the magnesium arm, and the magnesium arm will get blocked in there.
So, but what is the change? I mean, that is just, so I understand there is a moment when I have a higher voltage going to this neuron.
Yeah, so this
And
one's
then everything is back to
So it has to be repeatedly done for it to continue, but it will continue.
not necessarily, no, because it could be this could already be depolarized because I have another one of these on another part of the neuron from another neuron. So another neuron could have a synapse going onto this neuron here, which means this has already been a bit depolarized. So when this one starts firing,
And what happens then? I have a
well, then you've got
synapse
you've got more receptors able to receive the neurotransmitters coming from this synapse.
and then the question is, what happens then?
What happens? Did the magnesium ever come back?
Yes.
It comes back.
Yes.
But then
Under
what is
what
it
condition?
usually?
Well, when things have settled down, when this is
That's what I mean,
when this
so-
is less when this has gone back to its resting
So
potential.
that's kind of what I mean. So in order for the magnesium thing to stay gone, that would have to be continuous.
Yeah. So this is not a long-term solution to the increase in efficiency.
But it's a partially long.
It's the thing that gets the whole thing going. Yeah.
Another question:
But it does come back.
is it exclusive to glutamate?
No, I don't think so. Well, it is, this particular process is, but I think there are examples of long-term potentiation that don't involve glutamate, I should imagine.
I haven't answered that yet. I still don't understand. So this one is, it's already activated, it's firing, it's increased. I understand that.
Yeah.
So once it gets back to resting potential, the magnesium is replaced, and then what happens?
Well, that's what I'm going to tell you next.
Okay.
Okay.
I think there's a few behind.
Okay. Yes.
Sorry, I just don't.
Okay, so this is a neuron here, and this is a dendrite,
Yeah,
and this is a synapse coming from another neuron,
yeah.
and this is producing So these vesicles are opening up, and neurotransmitter is coming across here, glutamate is coming into here, there's a bit going into there, and that's increasing the positivity of this synapse. So it's depolarizing the synapse. But actually this synapse may already be a bit depolarized from another neuron. That's the coincidence. And if that's the case, then this magnesium ion comes out, increasing the flow of neurotransmitter and increasing the amount of receptor activity. There's more receptors now, and increasing even further the depolarization on this side. Why it's a coincidence detector, because it's a coincidence that this one is firing. There's glutamate coming across here through the AMPA receptors trying to depolarize it, but there's another neuron over here somewhere that's already depolarizing this one as well.
So should it be here? Should it be painted here?
Well, maybe it should be painted here, look. There you are. So there could be another neuron.
This end of another axis.
Well, okay, that's coming to another. So that is already depolarizing this a bit.
So this is a process of long-term.
This is the beginning of long-term potentiation. Just the beginning. I'm going to tell you what happens next now. Okay.
We were just wondering, so if, say this is a neuron and then another one, and then this is the process of long-term potentiation, so when you reach the neuron it's already active.
Yes.
Does that mean that the neural network has already widened and for a connection to have already reached that neuron?
Well, well, that could be working like that, or that could be coming from another periphery, another peripheral neuron. So in other words,
so more like this, so the stimulus could now be activating it, kind of like what you were talking about.
Yes, so it could be, that's right, it could be activating two neurons, and if those neurons are together, then the connection between them is going to become much stronger if they're both getting activated by the same stimulus. Is calcium modulated protein which enters the nucleus of the postsynaptic neuron, and that initiates a whole series of reactions that produces new receptors and can also produce new synapses. In the early phase, we see temporary insertion of new AMPA receptors as a result of those calcium ions triggering calcium modulated protein. And in the late phase, we see longer term changes, not only new AMPA receptors, but also new synapses forming. And that, of course, means a whole new connection. So, that's very important in terms of the longer term effects of learning. So I've tried to illustrate that here. We've got NMDA receptors and AMPA receptors that are receiving glutamate neurotransmitter. But also we've got calcium ions coming through here, and these calcium ions are interacting with the nucleus, which is then feeding back through a chain of processes the production of new AMPA receptors and, in the longer term, new synapses as well. New synapses with AMPA receptors and then NMDA receptors all ready for future learning. So those are probably the longer term changes that are responsible, because we have memories that last years, don't we? And we have to find processes that are going to be able to explain that enduring effect. So it really is the case that our experience, our learning, actually transforms us biologically. These are the biological changes that happen as a result of us learning, which is fairly incredible. So what we learn, what you've learned today, has actually biologically transformed you in some respects. Scary stuff. Yes. Yes. In terms of developmental changes, up to about 4 years old, we get this massive proliferation of synapses. And then we start seeing them dying back. But that's a bit simplistic, because actually the proliferation and the dying back, the pruning back, happens at different rates in different regions of the brain. And in some very important regions of the brain, the dying back process can go on till about 19 years old. I think that's what we were talking about last week, actually. And that dying back process, we also believe, is important for learning as well. It's not just the production of synapses. Oh, you have learned so much this morning. I'm very pleased and proud of you all. Yes.
So say when
Yes.
In terms of like say linking that learning with what we already know, are those synapses sort of linking back to that in some way, or is that completely
Well, you seem to be worried about this one-way direction of what's happening. Is that right?
not so much? I'm sort of thinking about how when you learn something new, then like you connect it back to like what you already know.
Yes.
It sort of it strengthens that learning.
Yes. So if you think about how that might happen, if you what you're saying is that you need to connect things. Yeah. So and that's one of the reasons possibly why activate learning, because you need to activate two things that are related, and when they're related, then the representation of them, the neural representation of them, is more likely to form connections between them. So that's very hand waving. We have to be very careful of that, because we mustn't start talking about ideas as if these are discretely represented in neurons, and that I can find this handful of neurons that codes for cat, and this this packet of neurons that codes for dogs, and they're both four-legged animals, so I must have another neuron that's connecting the two things. It's actually much more distributed than that. And even with quite simple neural networks, say that contain like 100 neurons that have been simulated, we can see how they solve these problems using this simple mathematical rule of coincidence detection, if you like. But when you look at the weights, the efficiencies of the individual neurons, trying to work out how our simple artificial neural network has actually coded these concepts is very difficult, because each concept is distributed, it's coded, it's represented right across every single neuron, if you see what I mean. So the complexity, even with 100 neurons, is difficult for us to interpret in a meaningful way, in a way that can be simply communicated. We have around 86 billion neurons in our brains. So it's, and if we're saying our ideas, our concepts are distributed across the brain, across those 86 billion neurons, it gives you some idea of how we should try not to simplify things, and start talking about connections between ideas as being the same as connections between neurons. Okay? Right, we're almost at our break. The best basis we have for learning is this, well, what evidence do we have that long-term potentiation explains learning? Well, we know that short-term memory to long-term memory transition needs protein synthesis to maintain the synaptic enhancement. So if you suppress protein synthesis, that production of calcium proteins, then we know that will suppress learning. So that's a pretty good indication that long-term potentiation is very important for learning. Mice treated with NMDA receptor blockers unable to learn their way around a water maze. That's more evidence. It's all quite indirect and circumstantial, though, isn't it? It's quite surprising that something so fundamental to our understanding of learning, which long-term potentiation has been, it still relies on evidence which is a little bit more circumstantial than we'd really like it to be. Another one is that using rats conditioned to freeze to a neutral sound, the synaptic potentials from the amygdala, which would be very involved in the fear response, become enhanced only while the learned response continued. Once they appeared unable to know it anymore, you don't see those synaptic potentials coming from the amygdala. And that enhancement can be mediated by glutamate receptors and are dependent on NMDA receptors. So if you knock those out, then you don't get that enhancement of the freezing. You don't get that learning continuing, essentially. So, there are many other experiments like that where they've shown that interruption or disruption of NMDA receptors appears to suppress learning. And of course, we now have drugs chiefly developed in terms of Alzheimer's research that interfere, if you like, more positively with some of these mechanisms and also appear to improve memory. So it's through those sorts of interventions that we have a fair idea that long-term potentiation is a really important basis for learning. But it is still early days in terms of completely understanding. I've got it says demo there. I don't know. Actually, I can't remember what demo is. No, it's not there. Okay. There are other learning mechanisms. So, such as, for example, long-term depression, reduction in the firing rates, e.g. in the perirhinal cortex, which is involved in face recognition with habituation. One of the things that happens when we get used to a face is that we get a reduction in activity in some regions of the brain, and that appears to be linked to long-term depression as opposed to long-term potentiation. And we also know that new neurons can now be born. We didn't know that a couple of decades ago. So, particularly in the hippocampus, and the hippocampus is very important for learning. What the precise role of these new neurons, this process of neurogenesis, is in learning, we still have to discover. Generally, we think of learning in terms of changes in the connections between connections between neurons, changes in the connections between neurons, but undoubtedly, neurogenesis has the potential to play an important role in learning as well. We just don't know what it is yet. So that's one of those watch this space topics. Right, so I do believe, before we go on to where is memory in the brain, we need to have a break. So I recommend coming back here in 20 minutes, which will be 10 to 1. Okay? 10 to 1.